So, this video will demonstrate with an example how to find two linearly independent solutions for a linear second order homogeneous equation with variable coefficients, for which you do not know early methods will not work. So, you look for I demonstrate the power series method to find these two linearly independent solutions. Okay. So, let us start with an example. So this is an example I do y double dash. If you want to solve this y double dash plus x y equal to 0, x is the coefficient, and this is, you can clearly see that there is all the points are ordinary points. This simply you have 1 is defined everywhere. So, there is 1 is never be 0 any point. So, you have all the points are ordinary points. So, the equation is defined for all values of x. So, and clearly p x is 0 and q x is x, both are having power series expansions already. They are polynomials, already they are power series, okay, with other remaining other coefficients are 0. So, 0 and x are, you have power series representations. It is also valid for every x belongs to R. You have a power series representation which is valid minus infinity to infinity, R equal to minus infinity here around 0. So, you look for your solution as C n x power n, n is from 0 to infinity. Okay. Then you can differentiate, assuming that you can differentiate y dash of x. Why you are able to differentiate here? So, this is how you look for your solution. But you see that this solution, after substituting into the equation, this theorem will give you that you have a solution. So, you have a power series solution that is also valid wherever this p and q are converging. Wherever these p and q are converging, y is also converging. Okay. And a priori I know that p and q here in this case is actually valid everywhere. So, you will get that this power series is actually converging everywhere. So, once you have a convergence, you take any closed interval every time. You want this point, at this point you want convergence, you want to differentiate at this point. So, you simply have a closed interval. Once you make a closed interval your power series, the convergence is guaranteed by the method, by this theorem, and actually the convergence is uniform because your domain is a closed interval. Okay. So, once is the uniform convergence here, so I can do term by term differentiation here. So, like that you can see, because if this point x I choose and here is arbitrary, I can choose whatever may be x value, I can always enclose with a closed interval over which the power series convergence will be uniform, implies I can do term by term differentiation for power series. So, y dash x is simply term by term differentiation. The derivative of this power series is simply C n into x power n minus 1, but you need y double dash. So, you can do one more time, because again this is a power series which is also converging. Okay. Again that is from the property of the power series, this converges uniformly wherever it is convergence, power series convergence. Okay. The same with the same argument, y double dash of x also you can calculate as a power series, as a term by term differentiation, n is from 0 to infinity n into n minus 1 C n x power n minus 2, and you see x is actually, when you differentiate once, a coefficient of x power 0 will not be there. So, that is running from n is from 1 to, this is from 2 to infinity. Okay. So, even though when n equal to 0, it is like 1 by x, n is here. So, n is here. So, n equal to 0 also, if I put n is 0 into c 0 into x 1 by x. So, that is anyway 0. So, this does not matter. Okay. So, you can also include 0, because this 0 and 1, these two will take care, make it 0. Okay. Now, this you substitute into the equations. In your equation, if you substitute, n is from 0 to infinity, n into n minus 1 C n x power n minus 2 plus x times sigma n is from 0 to infinity C n x power n equal to 0. So, I have to find this constant C n's. Okay. So, this gives me, see, this is my x power n. Okay. So, it is just rewrite n is from 0 to infinity n into n minus 1 C n x power n minus 2 plus sigma n is from 0 to infinity C n x power n plus 1 equal to 0. Okay. So, you make common powers. So, I have n plus 1, I have n minus 2. So, n is starting from n is from 0 to infinity, right. N is 0 to infinity, I have x power n plus 1. You make this power as x power n plus 1. So, if you want n equal to n plus 1, what happens? I am going to change the index. N equal to, I am replacing with n equal to n plus 3, right. For n equal to n plus 3 minus 2. So, that is going to be n plus 1, n plus 3 equal to 0 to infinity, n plus 3 minus 1, n plus 2 c n plus 3 x power n plus 1, okay, plus sigma n is from 0 to infinity c n x power n equal to 0. So, once you have this n equal to n plus 3, this is running from minus 3, right. So, n equal to minus 3, you have this c n x n plus 1. So, n equal to minus 3, this anyway 0, n equal to minus 2, this is also 0, okay. So, is actually it starts from n equal to minus 1, okay. That is what is the series. So, what is the isolated terms? N equal to minus 1. So, that means n equal to minus 1 means 2, n equal to minus 1, that is 1, 2 into 1, c n equal to minus 1 is 2 into x power 0, n equal to minus 1, plus what I have is n is from 0 to infinity, n plus 3, n plus 2, c n plus 3, okay, that is the common, plus c n. I am combining with other power series into n plus 1 equal to 0. Because they are uniform convergence, two power series is also converge, you can combine it, you can add and subtract, okay. So, this is what you have. So, this is what is the power series. Now, this is true. You see when the power series is 0, some c n x power n, n is from 0 to infinity is 0. How do I calculate what are the values of c n? Okay. You differentiate. So, you put x equal to 0. If you put x equal to 0, c 0, which is 0, okay. You differentiate n into c n x power n minus 1, this is the power series expansion equal to 0 again. Now, again you put x equal to 0 for n equal to 1. So, that makes it c 1 equal to 0 and so on, okay. You can always do. So, when you make the power series 0, so what you get is the coefficients are always 0, you can just equate the coefficients. You do the same thing here. So, I have the power series, okay, n equal to 0 means it starts from x 1 onwards, x power 1, x power 2 onwards in this power series, and here x power 0 terms are here. So, I can just simply coefficient of x power 0 and coefficient of x powers, I can make it 0. So, that makes it c 2 is 0, okay. This part will be 0 or n plus 3, and here n plus 3, n plus 2, c n plus 3 plus c n has to be 0 for every n equal to 0, 1, 2, 3 and so on, because it is running from 0 to infinity. This is called recurrence relation, recurrence relation of power series, okay. And the power series method, you get this recurrence relation, c 2 is 0 you found, and I have to find what. So, put n equal to 0. So, if you put n equal to 0, 3 into 2 c 3 plus c 0 equal to 0. So, that gives me c 3 equal to minus c 0 by 3 factorial. Put n equal to, by putting n equal to 0 into the recurrence relation, putting n equal to 1, what happens? N equal to 1, 4 into 3 into c 4 plus c 1 equal to 0. So, this will give me c 4 in terms of c 1 divided by 4 3, Okay. So, this is what you have. So, now n equal to 2, if you put 5 4 C 5 plus C 2 equal to 0. So, that makes, because C 2 is 0, C 5 should be 0. Okay. N equal to 3, you get 6 5 C 6 plus C 3 equal to 0. So, that will give me C 6 as minus C 3 by 6 5. So, you write 3 to 2 only. So, no factorials. So, this is equal to minus minus plus is going to be C 0 divided by, because I know what is my C 3 now. C 3 is 6 5 3 2, 6 5 3 2 with minus 1 square. Okay. So, it is plus basically, minus minus plus and so on. So, you also write n equal to 4. If you see the pattern, you can find the nth term C 2 n, right. So, you can write C n, you may get C n in terms of C 0 or C 1. So, write like this, you get n equal to 4, you get 7 6 C 7 plus C 4 equal to 0. So, this will give me C 7 as minus C 4 by 6 7 or 7 6. This is minus minus plus C 1 divided by 7 6 4 3, 5 is missing, okay, and so on and so on. So, I know pretty well C 2 is 0, C 5 is 0. Next thing will be, next thing is C 8 will be 0. Every 3 terms will become 0. I have C 0, C 0, I am not able to calculate. So, they are arbitrary, they can be anything. Okay. So, you can write now your go back and substitute into your yx. Yx is C 0 I do not know, C 1 I do not know, C 1 x, C 2 is 0, C 3 is what? C 3 is minus C 0, minus C 0 by 3 2 x cube. C 4 is minus C 1 by 4 3 x power 4. C 5 is 0, C 6 again plus C 0 divided by 6 5 3 2 x power 6, right, and then plus C 7 is C 1 by 7 6 4 3 x power 7 and so on. C 8 will be 0 and so on. Okay. This is what you got. So, this is now everything is in terms of either C 0 or C 1. So, collect the coefficient of C 0, 1 minus x cube by 3 2 plus x power 6 by 6 5 3 2. So, every time you calculate again you can expect minus and dot dot dot. Okay. So, you should have minimum when you write the series, if you know the nth term you can write it nicely as a sum, otherwise you should have minimum 3 terms and then dot 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 plus C 1. C 1 you have x minus x power 4 by 4 3 plus x power 7 by 7 6 4 3 and then minus dot dot dot. So, this is what you have. So, this is your yx, where C 0 and C 1 are you could not find. So, they are still arbitrary constants. So, these are your solutions. If they are arbitrary constant means C 0 I take it as 1, C 1 I can choose as 0. Okay. That implies if I choose this I have one solution, that is also a solution, right. So, y 1 x will be 1 minus x cube by 3 2 plus x 6 by 6 5 3 2 minus and so on. So, this is one solution, and if I choose C 0 equal to 0 and C 1 equal to 1, you can get another linearly independent solution, that is x minus x power 4 by 4 3 plus x 7 by 7 6 4 3 minus and so on. Okay. This is a minus starts and then dot dot dot. So, this is another linearly independent solution. These two are linearly independent because one is starting with 1, other starting with x. Okay. X cube, x 6 you do not have other things. So, obviously, they should be linearly independent. So, you have implies the general solution of the given equation. General solution is yx is C0 is an arbitrary constant with y1, which is a power series itself, and another arbitrary constant into other power series solution y2. So, this is your general solution of the given differential equation. This is how you can find two linearly independent solutions, but they are not in a analytic form. So, you have they are in a power series form. Okay. So, we can do this exercise, you can try to find. So, you can see now the another thing is these power series, as I explained earlier, because these px qx, this px qx, these coefficients of y dash and y 0 and x, which are valid for a full real line, the power series is also converging in the full real line. So, actually you have a convergent power series. These series are actually convergent for every x. Okay. So, this is actually finite, this is actually finite, this series is actually finite for every x in fixed, for every x in R. You put every x in R, this series will be finite, okay, because that is how you calculate it. Okay. So, you can actually show that if you work with the general equation, you can see that what you get a power series by looking at its convergence from the convergent test. For example, ratio test, you can actually show that as you will get radius of convergence will be full infinity. So, that means it is converging everywhere. Okay. So, in this I will just explain before I go for another example, we will explain what is the radius of convergence of a power series. Radius of convergence I have not given earlier. So, you have a power series Cn x power n is from 0 to infinity. Okay. So, from calculus, if you know that Cn plus 1 by Cn, nth term x power n plus 1 by x power n. So, n plus 1th term divided by nth term, you take the modulus. This limit n goes to infinity. If this is 1, then a series is converging, right. So, this means if this is greater than 1, a series diverges. If it is equal to 1, you cannot conclude. Okay. No decision, not this. Okay. So, convergence, divergence, no result. You cannot say anything here by getting, if you get like this. So, what is this left hand side? Left hand side is actually equal to x goes, you have a mod x times this limit n goes to infinity Cn plus 1 divided by Cn. Okay. So, this is your left hand side. So, if this is equal to this, that means if this limit I calculate as n goes to infinity. Okay. So, what is this? This means if this mod x is less than 1 divided by limit this Cn plus 1 by Cn as n goes to infinity, for I get convergence of the series. Okay. If this is greater than this limit, so set of all x values for which this is what you get the convergence. If I use this inequality. Okay. If I use this inequality, you will get a divergence. So, if mod x is greater than 1 by limit n goes to infinity this Cn plus 1 by Cn, you get divergence. So, what is this one? So, this will give you, this is actually nothing but limit of this 1 over this means actually limit of Cn divided by Cn plus 1. Okay. So, convergence, this is exactly, so radius of convergence is mod x is less than r, this if you call this r, that is the radius of convergence, that is 1 divided by limit Cn plus 1 divided by Cn as n goes to infinity. This is nothing but limit n goes to infinity mod Cn divided by Cn plus 1. So, you can actually calculate this limit and say that this is your radius of convergence. If this is infinity, mod x less than infinity, any value, that means any real value, you have a series is converging. Okay. If this real value is becoming 0, suppose this is becoming r. Okay. If you for all mod x, if this is this is same, right. So, if this is a 0, anything greater than 0, mod x is greater than 0, the series is diverging. That means the power series is converging only at the value at x equal to 0, but anything outside is not converging. So, radius of convergence will be 0 in that case for the divergence. If this has a finite thing, so if you know that if this is this limit is not infinity, if c is some finite number, then the mod x less than r, that means mod x between minus r to r, x is here, x belongs to this, the series c n x power n is from 0 to infinity converges. That is what is the meaning of radius of convergence. Okay. So, radius of convergence of the power series you can always calculate from the ratio test of a number series. So, fix your x, this is what happens, you know this. Okay. So, if you fix it, this is what happens. If this quantity is less than 1, you have a convergence. That is exactly saying same as saying mod x is less than this, mod x is less than this, convergence. That is mod x is whatever quantity here, that is the radius of convergence. Okay. Let us look at some other examples. Let us see only what the equations are. Okay. So, can have a problems like finding or write classify the singular points in the for the equation. Okay. Given equation. So, let us say x cube x square minus 1 y double dash minus x into x plus 1 y dash minus x minus y 1 into y equal to 0. Suppose this is your equation, and you can see that this is the a naught of 0. So, a naught of x equal to a naught of x is x cube x square minus 1. So, this will be 0 at x equal to 0, x equal to plus or minus 1. So, you have 3 points. So, other than these 3 points, all points are other than these 3 points, all other points are ordinary points. Okay. So, ordinary points all ordinary points are set of all x such that x is not equal to 0, x is not equal to plus or minus 1, a set of all x in R such that these are ordinary points set. Okay. 0 plus or minus 1 are singular points. So, this is what I explained what do you mean by ordinary points or singular points. But you have 3 singular points and they may be in some nice form. Those points may be in some order, some better order, so that you can actually find a power series solutions, okay, later on. So, what do you mean by those singular points? If it is a regular, if it has some regularity, some order it has, if the singular points has some order, some kind of order, okay, if it has the structure, if it has, then you can actually go for similar kind of power series solutions, but this is called Frobenius method, we will see later. So, we will classify them before by looking at the equation. Once you see that you have a singular points, when they are regular singular point, when they are not, we will see. Okay. So, what we do is we divide this equation here both sides. So, if I divide this equation, we will get y double dash minus x into x plus 1 divided by x cube x square minus 1 y dash minus x minus 1 divided by x cube x square minus 1 into y equal to 0. So, this is what you have, the equation becomes this. Okay. So, once you have this is actually equal to y double dash plus minus x goes, I have by x square, and this becomes x minus 1 over this y dash minus 1 over x cube x plus 1 into y equal to 0. Okay. So, what is my p? P is 1 over x square into x minus 1, and q is minus 1 over x cube into x plus 1. Clearly 0 and minus plus or minus 1, plus or minus 1, either 1 or minus 1, they are singular points, because p and q will not have power series representation at x equal to 0. Okay, x equal to 0, because at x equal to 0 you cannot write, right, x equal to 0 you have a problem here. So, x equal to minus 1 also will have problem for q, x equal to 1 p has a problem. Okay. So, if you consider the domain 0 minus 1 plus 1. So, if your domain is this, no issues. If your domain is here, there is no problem, otherwise you have an issue, or your domain should be this or this. Okay. So, what happens if I am looking for, if I want solutions is 0, 0 is a regular singular point or not. So, if you actually expand this as a power series, my px, px, if you can write it as a power series, okay, you can write this as a power series. If I have x times px, see the motivation is coming from Euler-Cauchy equation, that is x square. So, let me call this coefficient, I take it as 0, okay, y double dash plus x times y dash plus y equal to 0. This is Euler-Cauchy equation. You see this one, if I divide this a naught, this a naught is ax square. If I divide this, x by x square is 1 by x, and here 1 by x square. So, if I have the singularity like this, okay, 0 is a singular point, I can still look for solutions for x positive. So, I know how to solve this one. So, this gives me a motivation, this equation, y double dash p is this and q is this. Okay. Here my p is this, q is this. If p is in this form 1 by x into x, which is 1, okay, here x into 1 by x, which is 1, which has a power series. Similarly, x square into q, which is 1 by x square, so which is 1, which has a power series. So, in the same way, if I have x into px, similarly x square into qx, if these have power series, okay, around x equal to 0, these two have power series around 0, then the 0 is a regular singular point, That means what happens? If this has a power series, what happens? This will have Cn x power n, n is from 0 to infinity. Now, if I take this limit x goes to 0, this x goes to 0, that means some C naught, which is finite. Okay? I already have the power series, I know what is my Cn's here. Okay? Once you have a x into px has power series, I know all the coefficients. So, if I put x equal to 0, that is same as finding this limit. Okay? So, you have, so this means this is a power series means, so another way of saying is you have these two limits exist. So, this is another way of saying, that implies if this limit x into px, limit x goes to 0. So, 0 is the singular point you are looking at it. So, this is, if this is finite and this limit x goes to 0, x square into qx, if this is finite, then your power series, both will have power series, right, no issues, right, power series, then 0 is regular singular point, Okay. So, now let us see by looking at px, what is my x into px is, x into px will be 1 by x, x minus 1. So, what I have is x into px, if you want to see as x goes to 0, this is equal to limit x goes to 0, x into minus 1 divided by x into, so this will be x into x minus 1, and this limit is actually not finite, this is actually infinity. Okay. Again you can look at this other thing, x square into q x. So, this limit x goes to 0, q is again, so you have a minus 1 by x square, minus 1 by x square x plus 1, this also infinity. So, both the limits are not finite. Since this is the case, 0 is not a regular singular point. Okay. In this example. Okay. So, for this example, this is what is the case. What happens at x equal to minus 1 and plus 1, you can see. So, to do that, you simply look at x goes to plus or minus 1. First you start with 1, x into p x, that is simply limit x goes to 1 minus 1 by x square x minus 1. So, this you have to put it as x minus 1 into p x as x goes to 1, right. So, this will have this goes. So, what you have simply left with is minus 1, which is finite. And what is the other one? X goes to 1, x minus 1 square into minus 1 by x cube x plus 1, because here also this is finite, this limit is actually 0. So, that is finite. So, implies since this is the case, you have regular singular points. So, minus 1 is plus 1 is a regular singular point, regular singular point. Okay. So, this is how you classify. So, even though you know that certain points are regular singular points, you can see them whether they are singular, whether they are regular or not, okay, by just calculating some limits. Okay. What do you mean by limits? So, if by doing these limits you are just calculating the power series around those points. Okay. So, x into p x, you are looking at x into p x, x square into q x. If they have power series around 0, 0 is a regular singular point. If you want a power series around x equal to x naught, in general if you want, so you say that x minus x naught times this one. So, this and here x minus x naught square into q x have power series around x equal to x naught. Okay. That means p and q are allowed to have 1 by x minus x naught and 1 by x minus x naught square, maximum singulars. Okay. Not more than that. They are not allowed, this cannot have more than 1 by x minus x naught power square. Okay. So, negative powers cannot be more than minus 2 minus 1 maximum. Here this negative powers for p x maximum minus 1, right, x minus x, that is the meaning. Okay. So, that is then you say that this is x naught is a regular singular point. This is in general, this is what we see. If you put x naught equal to 0, that is what we have seen for the Euler-Cauchy equation. So, now what we are left with other part, that is minus 1. You look at this minus 1 means x minus x naught is minus 1, x goes to minus 1 times p x. This is simply x goes to minus 1 by x square x minus 1 x plus 1, numerator is x plus 1, I am writing here. So, this is also clearly 0, this is finite, no issues. Again here x goes to minus 1 x plus 1 whole square times minus 1 by x cube x plus 1. So, this I can cancel 1 and still again 0. So, this is also 0. So, no issues. So, minus 1 is also a regular singular point. Okay. So, that implies 0 plus or minus 1 are singular points in which plus or minus 1 are regular, but 0 is not. 0 is not a regular ones. regular points, regular, but it is not regular one. Okay. 0 is not regular one, that is what you have seen, right. So, this is what you have seen 0 and 1 is a regular singular point, minus 1 is also regular singular point. Like this you can classify certain equations. So, you can classify certain equations. In the next video we will see other examples how to find the two linearly independent solutions of second order linear equations. Okay. Linear homogeneous equation, you can by using the power series method we will find the solutions. Okay.